to the NMR workshop. What we will do now is the question number 2. Okay? The question number 2, basically what it's telling us is that we have this compound and this is the NMR of this compound. We have to assign all the peaks through a combined chemical shift and coupling constant analysis. Okay? Well, these are the spectra, okay, a simplified spectra of the spectra that you have. Basically, I only draw it, the section where are the peaks. Okay, and we have 4 sets of signals. One at 4.5, one at slightly lower than 4, one at lower than 2.5, and a singlet around 2, or even less. Okay, the integration that we can get it directly from the NMR is 2 to 2 to 2 to 1. Okay, and the first thing is to try to identify which protons we have in our compound. If we analyze this, we have 4 different protons, okay? These that we will say Hd, that are the 2 hydrogens that are in this carbon, and both are equivalent. That means that will be exactly the same. This signal, then we have these 2 hydrogens, Hc, that also will be equivalent. The 2 hydrogen of this carbon that will be equivalent again, and will be Hb, and finally we have the hydrogen of the alcohol. And we know that the integration of the protons of a compound are proportional to the number of protons. That means that if we do this, these 2 Hc will be 2 integration, Hc 2 integration because they are 2 protons, Hb 2 integration, and Ha 1 integration. That means that clearly only by the integration what we can know is that this signal, that is a singlet, will be Ha, because it's the only signal that integrates 1. Okay? Now, what we have is the other 3 signals that integrate 2 that correspond to Hb, Hc, and Hd. We can do the coupling constant of each one. For example, Hd will couple with first with the fluorine, and we will get a doublet. Okay, because Hd is coupling with the fluorine. Fluorine is the spin half, and that means that the hydrogen will couple with 1 fluorine, we will get a doublet. And then Hd is coupling with Hc, okay, that is a J3, and each signal will become a triplet, because our 2 protons, the spin is 1.5, that means 2n plus 1 equal to a triplet. Okay? And we know that the integration of these triplets has to be 1 to 1, 1 to 1, and these 2 triplets will be 1 to 1. Okay? Then we can check, for example, Hc will couple with Hd, and we will get a triplet, and can couple with, I will put it in the other direction, Hc will couple with, for example, Hd and J3, we will have a triplet, then can couple with Hb, we will have, each of the signals will be a triplet, sorry, okay, we will have a triplet with HD. Then is coupling with HB, sorry, and will be a triplet of each signal. Okay, and finally can couple also with the fluorine, is a J3. That means each of the signals will be a triplet of triplets of doublet, or a doublet of triplets, up to you. What we will have is a very difficult signal, okay? Because probably all of the signals will overlap one over the other, and will be very difficult to know which is the coupling constant. And finally, we have HV. HV will couple with HC only, and we will get a triplet. Okay, is not coupling with HA because normally acidic protons are not coupling with the hydrogens. Okay, in some cases could couple, but the most common case is that acidic protons like from OH, from NH2, from carboxylic acid are not having a coupling constant with the other protons of the molecule. Then basically, only with this data, what we will know is that, or what I can assign is that this will be HB, because it's a simple triplet. This, that is a doublet of triplets, will be HD, and this coupling constant that looks like a multiplet will be HC. The most complex signal will be HC, that corresponds to the coupling of HC with HG, HC with HV, and HC and the fluorine. Okay? Then, in order to know the coupling constants, what we can do is take this signal, these two triplets, okay, we have two triplets. We have two coupling constants. Remember that this is coupling with we will have the coupling Hc fluorine and the coupling Hg Hc. Okay? The fluorine is a doublet, that means in order to know the J of the coupling, basically what we need to do is, for example, take this will be the JF, okay, because it's the coupling between the doublet, while this coupling will be JHDHC. Okay? Then if we do the numbers, JF is $108.66, and this signal, the major peak of the triplet, is 1,821.39. That means if we do the math, we rest one of the other. If I am not wrong with my math, what we have is 47.70 Hertz. That is the coupling constant between the fluorine and HB. Okay? Obviously, it has to be the higher coupling constant because the fluorine is directly attached to this carbon. That means it's a J2. Okay? If if we do this math to calculate the coupling constant between HD and HC, what we have is 180.74 okay. And the coupling constant is 6.6.75 hertz, if I don't do wrong the maths. Okay? Remember that when we have this type of doublet of triplets, to calculate the coupling constant of the doublet is between the two triplet signals, we can take any of this distance, is the distance between the major peak and the major peak, or the first peak over the first peak, or the last peak over the last peak. All these signals are okay. You can take all these pair of signals in order to calculate the coupling constant. And in order to calculate the coupling constant of the triplet, we can use this distance, or this distance, or this distance, and this distance. If everything is okay, it has to be exactly the same number, or very similar. Okay? And then we will analyze the signal that is a triplet. Okay? We only have one coupling constant, that is HB HC. Means it's this proton that is coupling these two protons that are coupling with these two protons. Okay, and in order to calculate the J coupling, what we have to do is exactly the same than before. We analyze, for example, this distance, or this distance is equivalent. Okay? And if we do this, well, what we have is the signal in the middle is 1526.18, and if I don't do the maths, if I do the maths well, has to be 6.05 hertz. Okay? And in this signal here, we will see is the doublet of triplets of triplets. Okay, probably, by sure, the coupling between HC and fluorine will be the higher one. Okay, and then we will see like the overlapping of these two. If the coupling constant between HC, HD, HC, HV are very similar, like looks like here, what we will see is a doublet of quintuplets, more or less, okay? because these two coupling constants between HC and HB are very similar. And then what we will see is that overlapping will give us a doublet of quintuplets, where the coupling constant will be HBHC, HDHC will be very similar, around 6 point something, while the coupling constant between these two will be the bigger one. We can calculate, if you want, the coupling constant between the two big signals. We take this distance, okay, between the two top peaks, and if I do it well and I take the right numbers, this J fluorine HC will be equal to 796.43 minus 7769.54. That means that the coupling constant will be around 27 hertz, 26.91 hertz, if I do the math well. Okay. While the two other coupling constant will be around these two numbers. Okay? Basically, the technique that we are using in order to solve these problems is, first of all, we identify which protons we have in the starting molecule. Okay, with the integration, we try to see which compound can be assigned, which signal can be assigned directly, and then basically we analyze the coupling tree of each proton by separate, and we assign the signals to each proton by his coupling tree. And then the only that we need to do is to calculate the coupling constants. We take the easy signals, the simple signals. For example, this triplet is very clear, it's only one coupling constant. That means it's very easy to determine which is the coupling constant. Then we take this doublet of triplets, that also is very easy to determine the coupling constant. And finally, we will analyze the most complex structure. Okay? And that's all. Thank you very much, and see you in the question number 3.